So good morning and happy Thursday. How's everybody doing? Good, good. I see that more of you have submitted the project number two, but some of you have not, more than I anticipated. How's that going? All right. So don't wait till the last minute, right? Um, it's a total of 2 weeks to work on it. And in general, please get in the habit of starting early and do not hesitate to reach out. But there's only so much that I can do for you if you wait until the last minute. It's due this evening. So today, the plan is to talk about material from chapter four, specifically how learning works in complex environments. But before we begin, the usual administrative bits. Project number two is due this evening. Homework number one has been released. There are two different versions, one for the undergrads and one for the 4+1 grad students. If you are an undergrad, your grade for the grad stuff is excused, and if you're a grad, your grade for the undergrad stuff is excused. I did try in Canvas to do an assignment where it's assigned to subsets of the class, and that failed, right? It didn't work. For some reason, it was hiding it from everybody, which was weird. So the alternative was to implement it by excusing those cohorts from the assignment that wasn't for them. Okay. All right, so please take a look at that. For the undergrads, it is some hand exercises to reinforce stuff we've done about informed and uninformed search. And for the grad students, it's a small experiment and implementation and design for bidirectional search. And for that bidirectional search, you're given a series of more complex mazes, and you'll be verifying the theory of the performance improvement afforded by bidirectional search. Okay. Any questions? No questions? No? Everyone have a good breakfast? Get your coffee and all that stuff? All right, good. All right, so why don't we jump right in? So the next one, all right, to get you warmed up a little bit, and then we have an exercise after this. So I'll ask you, what do you call a fly without wings? What would you call a fly without wings? No? Tenzin? Oh gosh. You've heard this before? Yeah. All right. Yes, you'd call it a walk. Okay, very good. All right. And it took a long time to create this figure. All right. All right. You'd call it a walk. All right. So going on to the actual material, we have a cutaway of an eight puzzle problem, and we have a starting configuration. And the part I forgot to give you is the goal configuration. So let me just draw that in. And so for this goal configuration, I'm going to go with the standard given by the book, which I disagree with, but for consistency's sake, I'll respect that. And the standard for the book has a blank here, one, two, three, four, five, six, seven, and eight. And so this is our goal. And so from before, we had two heuristics when we talked about domination and improvements for A-star search and heuristic searches in general. If this is our goal, and we have two heuristics from last time, heuristic H1 counts the number of misplaced tiles, and heuristic H2 counts the distance to the goal location for a state, and where distance is measured as the sum of the Manhattan distances for each tile to what its goal position should be. So let's have you kind of, habituate on this a little bit, and we're going to think, at least just for this first expansion of the frontier, look at what the function would be. F of n is equal to g of n plus h of n for each one of these encountered nodes, right? So I'll give you a minute or so to think about that. We'll just go around the room and have y'all do some talking, okay? All right. So we'll first turn our attention to H1. Okay. And decorating the edges of this search tree, search problem, we have all of the moves that you could make from the starting state. This is our start. And in this case, when we say up, down, left, or right, we think about moving the blank, right? And so it's a motion of the blank that we're alluding to with these actions. Okay, so for H1, we're going to write down what that value is. Well, first, let me ask you, what is G of n? What do you think G of n is? If we make one move, Colton, it would be one. So we're going to write a one, a one, a one, a one. Okay, good. So now we'll look at this H of n, specifically H1. So if we look at our goal and we look at this left-handmost child, what does H of 1 return? 7? Okay. Alexander? All right, so this is out of place. Um, 4 is out of place. 5 is out of place. The only one not out of place is 8. Okay, so we're going to get a 7 here. All right, how about here? Anyone care to put yourself out there? You're among friends. Um, yes, but in this case, when you compute the heuristic, and that's a great question, Chris, you're looking at the numbered tiles that are out of place, not the blank. Or you could define it as all tiles, right? But I'm assuming it's the numbered tiles. Hmm. Yes. Hmm. So yes, the one is out of place. How about the two? That's out of place. Okay. The four. Is there anything not out of place? The eight. So if only the eight's out of place, right? What do you think H of one is going to return? Seven? Okay. So it's seven. How about this configuration? We know the eight's not out of place. Is anything else not out of place? So everything else is out of place, right? So that's what? That's seven. How about here? I'm sorry, I didn't hear. The same? Okay, so seven. Okay. So let's look at H2. So for H2, it's going to be a little bit more, a few more moving parts to calculate. So for H2, all right, um, for the one, what's that distance, Manhattan distance? It's one. So I'm just going to write really small in each corner what the Manhattan distance is, so you can just add it up. So that's going to be one. Okay. How about the four? I'm sorry. When I have one ear covered up, it actually is hard for me to, from all the years of swimming, swam competitively, high school and college, one of my ears is kind of, not as good as it should be. So could you say that again? Two? Okay. Two. So this is two. How about the five? Two? Okay. Deuces. Okay. I have a 13-year-old, soon to be 14-year-old, so I'm starting to learn all the things, the cultural things, right? How about the two? It's two. It's also two. All right. How about the seven? Two. How about the three? One. The six? One. The eight? Zero. Okay. So we add all that up. That's three, 5, 7, 9, 10, 11. All right. So that's 11. I should have written down the rest of them. This is going to take a while, right? Um, so how about this one? So one is what? One out of place. How about the two? It's one out of place. How about the four? Two. How about the five? Two. The six. Two. The seven. Two. How about the three? One. And the eight. Zero. Okay. So that's four, 6, 8, 10, 11. Oh, 11 again. All right. How about this one? So how about the one? It's one. The two. How about the four? Two. How about the five? One. The seven? Two. How about the three? The six? One. And the eight? Zero. Okay. So that's two, four, five, seven. Seven and two is nine. All right. So this last one. All right. How about the one? One. How about the two? One. How about the four? How about the five? The seven? One. How about the three? One. The six? And the eight? Zero. So that's four, six, seven, eight, nine. Okay. So in this case, our f of n equals g of n plus h of n. This f of n returns for h 2. It returns, let me just write it next to it. That's 12. This is 8. This would be 8. That would be 12. This would be 8. This would be 10. This would be 8. And this would be 10. Okay. And so you'll notice in all cases, H2 is greater than H1, right? As we said from our example from last time, H2 dominates H1. And we said that the admissible heuristic that is larger in value is a better heuristic, okay? So in this case, all right, when we make our selection using H1, okay, the sound lab. Someone's really having a party in the hallway. But in the case of our selection criteria, we know that through H1, well, we'd pick this one, right? If you're adding them to the frontier in order and it's a priority queue, right? Um, if it's the case of H2, well, we're gonna pick this one. Again, if we're adding them in child order to the priority queue for a heuristic search, an informed search. And so in that case, all right, our H1 heuristic, we'll eventually get there to the goal, but we're going to explore more nodes, those parts of the subtree rooted here and rooted here, right? Likewise, but for H2, we're going to effectively prune away the subtrees rooted here and pursue those subtrees here, right? And so this is just to kind of show you that this idea of admissible heuristics, a better heuristic for admissible heuristics, a better heuristic is the one that dominates, the one that returns larger values, because that pruning action is greater. And you can think of that as a search contour projecting forward out in state space versus more of like a breadth first strategy. Does that make sense? Okay, great. Any questions? No questions? All right, let me see. Oops, let me release my pen here. Uh, there we go. The sketch pad grabs focus and takes it away from the mouse. All right, so we're talking about search, the final frontier. And many of the searches, we've talked about uninformed and we talk about informed search. We start at some node n, or starting node, and then we call get successors, and we expand the frontier again and again and again, and encounter nodes along the way. So this systematic approach for how you search is what we've been looking at. And the consideration, well, I'll ask you, is there another way to search? the systematic starting where you are and just exploring the successors and, selecting from the frontier. Could there be another way? Is there another way, Chris? Hmm. Hmm. So you could do it in the reverse order, right? And you have to know the goal. Okay, good. Anything else? No? Okay, well, this is the subject of today, right? Another type of search. Absolutely, there's something else. And in that something else, we're going to make use of randomization. Okay? All right. So what we've been doing so far is so-called systematic search. And systematic search, we start at some start node, okay, add it to the frontier, and we expand the frontier. And it took a really long time to make all these diagrams by hand. But anyways, so we expand the frontier by generating its successors, and those successors are bounded from above by the branching factor. And we take these nodes that we encounter and we evaluate them, put them in the queue, some sort of data structure, I should say, and then based on the selection criteria, pursue some next node. In this first case, ultimately, it's from among the successors. So then we take that best successor that we've encountered, we take it from the frontier and we expand it, revealing its successors bounded from above by the branching factor. And I'm getting paranoid about this thing disconnecting. So excuse me. Yeah, it's still connected. Bounded from above by the branching factor. Okay. And again, we encounter some new nodes, those successors of the second node. We add them to the frontier and we make our evaluative selection from some data structure. And we pick some next node to explore off the frontier. Okay. So again, once again, we generate successors bounded from above by the branching factor, and we take those and we add them to some data structure, make another selection. So we keep doing this again and again and again and again until we encounter the so-called goal contour. Now, that goal contour, the goal itself might be explored first, or it might not be explored first. But nonetheless, we know bounded by some optimal path cost we've been calling C star in the book, we eventually get there, right? Provided there aren't pathologies with the state space that this type of search will not work on. And so we get our goal, okay, and we're done, and we keep track of the paths that we encounter along the way, right? We incrementally add, build that path, and construct our plan by returning back that accumulated path, piecewise accumulated, back unto back. We return that rather once we encounter the goal. Okay. And so along the way, we pay attention to the reach states, and we can use this in more than one way, both to see the nodes to prevent us from revisiting certain nodes, but we can also use it to update the notion of best path should we re-encounter a node that leads to a better solution. Okay, so I kind of got my eye on you. With that, we have a machinery that we've seen that we can do all sorts of searches, and particularly for informed searches, by tinkering with the heuristic, you can encourage all sorts, or enforce rather, all sorts of desirable properties. So another type of search, so-called local search, it's similar, but it's not the same. Yes, it does explore the successors. Okay. It's bounded from above by the branching factor, but it proceeds a little bit differently. So let's unpack that a little bit. We again start with our start state. We put it on the frontier. We expand the frontier and it generated successors bounded from above by the branching factor. We also have a selection criterion that we use to pick the next node that we're going to explore. So we select one, and let's call that arbitrarily node n sub I. And node n sub I then becomes, because it is the best for some evaluation criteria for selection, it's the best node to pursue. Okay. So we look from the context of this state or node n sub I, and we generate its successors, again, bounded from above by the branching factor. And from that, we make again another evaluative selection. And let's call that best node that we just encountered. Let's call that node n sub j. Okay. So now, from the perspective of n sub j, we again expand its successors. We expand this node, generating its successors. And the hope is that we will eventually, with enough repetitions of this, reach the goal contour, ultimately, hopefully, finding the goal. Okay. Now, in this particular case, in this local search, there's no tracking of the paths. There's also no tracking of the reach states, be that for um, preventing the reoccurrence of states or for updating a notion of best path. In this case, our local search, you only see your neighbors. I don't know if maybe you're too young. Do you remember the movie Groundhog Day? You know that movie? Okay. So it's like Groundhog Day. You re-encounter again and again and again, not maintaining a notion of how you got there. It's just local. The only consideration at every try is the expansion of the frontier, the generation of the successors, encountering new nodes, and selecting one. Okay. So, my question to you to kind of motivate today, why would we entertain this? Why would one want to do this? We see how useful tracking paths and tracking encountered nodes can be. Why would we ever want to do this? Oh man, I remember it was Antonio and Antonio Anthony. No, I don't remember. Alex. I'm totally off Alex. Okay, so now I'm going to remember Alex and forget Antonio. I remember in pairs of things. Alex. Ah, to save some memory. So thank you, Alex. It saves memory. Absolutely. You're not tracking reach states and you're not really paying attention to nodes on the frontier. Because in the case of something like breadth first search, we put an exponentially increasing number of encountered nodes on the frontier at each try, right? Okay. Anything else? Memory. Anything else? Any other thoughts? Chris? Mm. Mm-hmm. Mm-hmm. So by engineering this selection criterion, quote unquote, suitably, um, you're not spending time exploring parts of the state space that might not be fruitful. Okay, great. No, I guess you already answered it. Is this useful? Does it always work well? No, it doesn't always work well. And as you alluded to, memory and with the right selection criteria, you're effectively performing pruning, right? For an ultimate savings. Okay. And so, like you said, it uses very little memory. At any moment in time, every iteration, you're holding on to a very small amount of information, the node you're expanding, and certainly its successors. But the other benefit is that this can give you reasonable solutions in very large state spaces. With so-called systematic search, just by sheer definition, having to hold on to all of the nodes in the frontier and all of the nodes in the reached data structure, if you have very large state spaces, those methods are going to fail very fast, right? And so this is one of those cases where you're trading off engineering practicalities against algorithmic progress, right? Because in the real world, you have to be able to compute it. Also, if you have infinite state spaces, a local search is more effective. So basically, local search performs well, I should say, performs better in all of those messy problems that you might encounter. right? Big problems, continuous problems, infinite state space problems, etc. Okay. Any questions? No? All right. So let's take a look at this idea of this local search. Now imagine, and I've only drawn it in three dimensions because I only have a screen. Imagine a state space. And the state space, for every state, we said we evaluate some measure, f of n, however you compose f of n. Okay. And so our state space, in typically most problems, which you've had some experience with at this juncture, it's vector valued. So for the notional ith state, you have the first position, second position, up to some dimensionality n, right? And so let me ask you, I think I had a note here to ask you a question. Give me an example from, say, the Pac-Man environment of a vector valued state space to hear your thoughts. An example of a vector valued state space. What pieces of information did you see on one of those types of problems? Alexander? Position, okay. The X, Y. Anything else? Chris? Mm, the corners, yes. And I'd add to that um, the food search problem, right? Because you had the uh, the eat status of each one of those pellets inside of the maze. And so as you moved, that state changed. If your move arrived upon a position in which a food pellet existed, um, that position in that vector representing the true false eat status of that pellet would change. So you can think of every state, if it's vector valued, as being an instantiation of values for each one of the positions in this vector. And so for each state, we said we have an evaluative measure, f of n, right? And f of n, we said in one example, is h of n plus g of is g of n plus h of n. Okay. So let's think in this example, our state vector in this example is a two-dimensional state vector. Might be x position, y position, doesn't matter what it is. And our evaluative measure, f of n or f of si, is going to return a value. And so we said for each state, you have a value. And that value collected together, you can think of as some function. And we said our selection criterion is to pick this notion of a best F value. Now, this best F value we've been talking about this far is the smallest one. It's a priority queue. That selection criterion says, I'm going to pick the one with the smallest value. Now, it doesn't really matter what your selection criteria is. It could be the smallest value, it could be the largest value. But in this case, if we're going to pick the smallest value, this lumpy surface you can think of as this function. For every location, every instantiation of state, we have a value in the z direction. The higher the value, the larger f returns. The lower the value, the smaller f returns. So if you're selecting in your priority queue the smallest value, that's essentially preferring solutions that go quote unquote downhill. Does that make sense? And so effectively, as you repeat these tries, select, 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 expand, select, expand, select, expand, select, you're effectively walking downhill. And the analogy, you can imagine taking a marble and setting it in that state or that position for your start state and letting it go and letting it roll downhill. Does that make sense? Any questions? No? So this function, this lumpy function, and again, I'm only displaying it in three dimensions because that plane, XY plane, as it were, positions there represent your state instantiations, and the z-axis projection represents that value of that function f of n. But certainly, your state description can be an arbitrary n dimensions, right? I just can't draw that. at all. Does that make sense? All right. Any questions? So you want to roll downhill on this so-called landscape, this objective landscape. And I use the term objective specifically, deliberately, is because it's a term from optimization. You're effectively trying to find a solution that is the minimum of some complex function. It's a lumpy function, yeah. It might not be a smooth differentiable function, no. But nonetheless, you're still trying to find the minimum of a function. Okay. And so essentially, what local search does is solves optimization problems thought of as a mathematical optimization problem. Now, with that idea, that opens up a whole host of all sorts of other tools beyond just finding your successor, finding your successor, finding your successor, limited by your branching factor from above. Okay. And so essentially, we're running this objective, this evaluative measure over the landscape, which is that function over your state space. Okay? All right. Any questions? No. Make sense? All right. And so another aspect of thinking of this as an optimization problem over some landscape is that you can extract all sorts of efficiencies that might save time or save space by considering features on this terrain. If you've taken some abstract algebra, if you can find isomorphisms or if you can find symmetries in features of this landscape, every time I go up a slope for a certain stretch and I have a plateau following that, I usually have a solution on the other side. So you can recognize certain pathologies about the geometry of your landscape. If you know that there are repeated structures, you can now cache away sub-plans of actions that deal with that. So by looking at various features of your terrain, thinking of it as a landscape, tools from optimization and abstract algebra can help you deal with the engineering issues about memory and about computation time. Does that make sense? Okay. But that's beyond the scope of this class. I just want to point it out to you that if you plan to do things at a graduate level or go off in industry, go to grad school and take more math, right? It's really, really important. A lot of beautiful and deep and interesting connections between all sorts of different corners of mathematics and AI and machine learning. Okay. I'll get off my soapbox for that pitch. All right. Anyways, so you can extract all sorts of features. This figure's from the book. It's a cutaway of a notional 1D function. And when you are doing so-called hill climbing, that's a synonym for pursuing the maximum. Now, in optimization, a maximization problem and a minimization problem are the same thing, right? Just through a transformation, you can convert the two. And you might wonder, why in the world would I want to convert it and solve a minimization versus a maximization? Because it might afford you tools that you might not otherwise be able to make use of, okay? But nonetheless, when you're pursuing the global maximum in your landscape, that means the biggest of the humps. And I'll explain more about what maximum and global maximum, what that distinction is. That's called hill climbing, right? You're trudging up the hill. So that means your selection criteria at each try is going to be pursuing that encountered node, your successor, that has the largest objective measure. Does that make sense? Any questions? No. And then gradient descent is the dual of that. That's a selection criteria on each try, criterion on each try, where you're pursuing the minimum. In the case of A star search, because it's a priority queue, you're going to select maybe the smallest heuristic f of n equals g of n plus h of n, and that's gradient descent. Okay. Now, with gradient descent and hill climbing, of course, from optimization and multivariate calculus. There's all sorts of tools you can avail yourself of to find solutions. So at the outset, when I pose that question, is there any other way we can do this? Absolutely. You can treat it as an optimization problem and find solution paths and extract efficiencies using tools beyond just looking at your successors. Okay. All right. Any questions? No? All right. And so this is a pseudocode for hill climbing. It's very simple. Um, and this is from the book. You start out with your search problem and your initial state, and you iterate over searching for the neighbors, the successors you generate, the highest valued successor based on your evaluative measure. And if it increases, then you pursue it. Otherwise, you stay where you are. Okay, looking for a better one. And this is where your Groundhog Day comes in. Because at each ply of the search or each try, you're not remembering anything. You're just looking at the context of where you are and you're only paying attention to the immediate neighbors. And so you have the so-called greedy approach, maximization. I'd also say minimization, just a negation, flips that. You have nonetheless a greedy approach at every iteration with a myopic view, only paying attention to what's happening immediately around where you are in the state space on this landscape. Does that make sense? Any questions? No? All right. And so this objective landscape, I'll draw that again. It was hell to make this figure, so I'm going to use it many times, darn it. You have many features. And some of these features for our conversation today, they matter because they're pathologies that confound this local search. And so a local maximum is a peak relative to its immediately surrounding neighbors in the landscape. And the problem with this local maximum, and I'll point that out here, you can see it, one of them noted here, local max. Where's my mouse? Over here. When you're doing hill climbing or this greedy search, greedy local search, it's going to get stuck, right? Because it selects the neighbor that is largest, okay? But once you get to this local maximum, there's no more larger neighbors. It just says, "Oop, I can't do it. There's no place else to go." Now, in any landscape, you're going to have many local maxima, and the smallest or the largest rather of the local maximum is going to be the global maximum. Conversely, if you're solving the minimization problem, gradient descent, you're going to have local minima. And so here on the graph or the landscape, we have a local minimum here, a local minimum here, another minimum here, and the smallest among the local minima is going to be your so-called global minimum. And so part of the problem with any greedy method, be it hill climbing or gradient descent, is how do you distinguish whether the minimum or the maximum that you're in is just a local one or a global one? Okay. Well, that's a problem. Yes, local search can solve the optimization problem. Yes, it's more memory efficient, but it doesn't know. It just knows that it's time to stop because you've reached some peak or you've reached some pit. Does that make sense? Any questions? No? All right. And so another feature that confounds greedy methods, hill climbing or gradient descent, is flat areas of a landscape. Now, of course, in practice, it's never completely flat, right? Maybe there's a little bit of an incline, but this little bit of an incline or decline is negligible, right? And in that case, your hill climbing or gradient descent is going to wander around. It has no idea where to go. Well, this is only a very, very mild increase, might be 1%, 2%, half of a percent increase, but it's not very dramatic. It's just going to jump around, right? So in effect, it's going to get stuck when you have these pathologies, these features in your landscape. Now, part of the problem is for practical considerations, even for a Pac-Man maze, you don't know the entire function in practice. Could you, for Pac-Man, knowing what your state description is, have a co-process that iterates through every configuration of your state space, evaluates the function, you have the whole function? You could, but For most, even medium-sized problems, that's going to be too big and take too long to evaluate. If you knew the entire landscape, absolutely, you could ahead of time evaluate your features, you could find isomorphisms, try to exploit stuff, but especially in the continuous case, right? You can't do that. Think about self-driving cars. You can't pre-compute what your what your landscape is going to look like. It's impossible. And moreover, in the case of self-driving cars, the world dynamics is non-stationary, right? Meaning that things change governed by a distribution, and that distribution changes, and it changes in ways that you can't anticipate, right? So in the case of greedy methods, well, there are some issues that can arise because of certain features, if you will, pathologies in your landscape. Another one is called a ridge. A ridge is a run or sequence of local maxima. Now, for greedy methods, be that hill climbing or gradient descent, it has a bit of a problem trying to get through that proverbial minefield of pathological shape of your landscape. It's difficult for these greedy methods. And so, to give you a really good visualization of a landscape of a ridge, I found a video in the spirit of the Winter Olympics. It's kind of like moguls. And poor, what's his name? Benjamin didn't do so well minimizing the search for this problem. I don't know why someone would ruin a perfectly good hill with moguls, but all of these lumps and humps, those are ridges. And Benjamin didn't do very well. I mean, they're still phenomenal athletes. I I would break my knees if I did this, but anyways. So you can think of a ridge as a set of moguls. And if you get stuck in a ridge or a plateau or local minima, you want to move sideways. You want to, and I don't know if this is giggle or jiggle. I meant to say jiggle, right? I don't know. But you want to move sideways. You want to not always make an optimal move going uphill or pursuing the steepest gradient. You want to move sideways or jiggle. Randomization can help you tremendously in that. Okay. So when we look at hill climbing, we have prototypical landscape. And you have your goal, you have a local maximum, and you have some peaks and you have some valleys. Okay. So you're in some location, you measure the gradient over your successors, and mathematically you can think of that as fitting a plane over this um, three-dimensional surface. And when you compute the local gradient, this difference between where you are and your immediate successors, you're basically measuring the slope along some plane in different directions fitted to this surface. So you take the gradient over your successors, and let's imagine your first choice is a maximum selection criteria. You're going to choose that successor whose objective measure on the surface is the largest relative to where you are, the steepest slope. Now, this can give you faster convergence, and like we saw before, if you have local maxima, you're going to get stuck. You're going to not be able to proceed because you don't have another max available to you. Where you are is the maximum among you and your neighboring positions. So you can get stuck. Okay. Any questions? No? And so what do? You jiggle it a little bit. You've reached your local maximum. Oh no. What are you going to do? You're stuck. All right. So you're going to jiggle it a little bit. So how do you jiggle it a little bit? Some variations on hill climbing, so-called randomized hill climbing, instead of selecting the maximum, you randomize your selection among all of those moves which are uphill. Now, some of your successors might represent gradient descent, right? They're at a lower objective value, but some of your successors might represent an increase or positive slope on your objective landscape. So in that case, instead of selecting the maximum, randomly select among those successors that are going to have a positive slope. They're going to increase in objective value. Okay. Now, yeah, that can work. And the reason why it can work, not always, but can work, is because you might find an alternate path. It could be that a solution path might involve some steps that aren't always the maximum direction, right? It's also going to be slower to converge because you're not taking this maximum. You might be, in effect, wandering. Oops. You might be, in effect, wandering around the hill, still going up, but not in the steepest direction. Okay. So that could work. Okay. Then there's also random restart. Now, with random restart, you're probing and exploring this landscape, hoping to find an alternate pathway. So random restart says, I randomly select a start state. Yeah, you're at a start state, but you randomly select a start state. And then you run hill climbing, this gradient ascent, stopping at a local maximum. And in the best case, you hit your goal. Okay, that's good. Then you select another random start state, perform hill climbing until you reach a local maximum. Then you select another random one. You do it again and again and again. And the idea is if you have many local maxima, one of them is going to be the global maximum. It's going to be the largest local maximum among all of the maxima in your landscape. So if you randomize the selection of a start state and run hill climbing, maybe, just maybe, one of these pathways might be in the vicinity of your global maximum. Now, then the problem becomes, okay, I'm in a start state. All I need to do is find a way to get to that path of that particular exploration seeded by that random start state. Does that make sense? Is it the optimal path? No, not always. But you know that there's some path that exists that can get you ultimately to that global maximum. Okay. Any questions? No? No questions? So whenever you're performing hill climbing, in order to get past being stuck in local maxima, you have to make a downhill move. Because if uphill is not working, sometimes downhill might lead you someplace which eventually gets you to that global maximum. And so, how you do that is by using some randomization. A random walk, which is what we saw with random restart, gives you multiple pathways. And if you find an alternate pathway from some randomized starting location, now it becomes a problem of getting to that path. Where are you relative to that path? Okay. Um, if you get stuck in local maximum, and I don't have this on the slide, there's something called Brownian motion. You take a randomized move in some direction, and that direction might not be a positive gradient. Ideally, well, many cases, it might be a walk down the gradient. So you're forcing you with Brownian motion a suboptimal move because sometimes you need to do something suboptimal, like go to college for 4 years instead of making money, right? In order to find a pathway that leads to a better solution, right? And of course, studies have shown in many cases, most cases, not all cases, that a college degree is still worth it, right? I promise you that being in this stage of my career. All right. Any questions? No? And so this idea of using randomization, and I can't possibly show you all variations of this. You could spend a whole semester just on approaches for randomized and semi-randomized optimization techniques. But how you control randomization can play a big impact on your ability to overcome local maxima and local minima, ultimately finding the global optimum. Okay. And so one of them in the book is called simulated annealing. And in simulated annealing, you're effectively controlling randomization. Sometimes you want randomization to be really big. It's going to make jumps to the far what's that word? Not extremes, excurts. I think it's excurts, all right? No, to the far extremes of your landscape. Other times, you're going to stay fairly local relative to where you are in your landscape. So this annealing, it goes from something from metallurgy, which is outside of my background and skill set. But effectively, if it's hot, you jump far. If it's cold, you jump a small distance in your landscape, and you control your temperature based on a schedule. And there are a whole host of ideas about how you control the schedule. And so you start in large jumps, and I have a soundtrack for everything. Nope. So we jump. Okay. So we start with our temperature on a hot schedule and we jump around. And in the beginning, this temperature is high. And in the end, this temperature is low. Big jumps when it's hot, small jumps when it's cold. And so when you take big jumps, you can think of it kind of like random restart. You're probing the extremes all around, swinging wildly across the energy landscape. And then as it cools, it's almost like hill climbing, like the greedy approach. You're not going to jump around very far. You're going to stay very local. And a special case of jumping locally is just searching for the maximum or the minimum on each try. And so this idea of jumping around is controlled by two things, a notion of a badness measure and the notion of the temperature. Because if you find that your jump is not producing dramatic improvements in your pursuit of something that's bigger or smaller, then maybe you want to increase the size of your jump to go to a different region of your objective landscape. If you find your jump is producing a quote unquote good improvement, be that minimization or maximization, you want to stay there for a little bit. So you're not going to jump very far. And so this idea of a badness measure looks at the change in objective measure after you take your jump. And you can use literally use that to shape the size of the next jump. And so, in effect, what you're doing is you're probing parts of your landscape looking for what's called a basin of attraction. Is there some part of your landscape that's producing desirable sequence of objective measures? If so, you want to walk down the gradient there so it looks like hill climbing. But if it's not producing good improvements on your objective measure, then you want to just cut your losses and go to some other neighborhood, so to speak, some region of the landscape. So large changes give you a big jump, small changes give you a very little jump. Does that make sense? All right. Any questions? No? So you're effectively probing. Just like random restart did probing, here are simulated annealings probing. And at each try of this local search, you're looking at the improvement afforded by that jump and adjusting that probability accordingly. That's defining how far away you're going to jump in your landscape. And so if you think about it, your states in your state space, in Pac-Man, when we had the eat status of the food, well, for a particular food pellet, when it is false, hasn't been eaten, is very close in the state space to true when it has been eaten. So if you're going to jump, you could maybe jump some distance um, relative to one food position, or something where maybe a stretch of 10 food pellets reflected as 10 food pellets being changed in eat status. Does that make sense? Are there any questions? Chris? Hmm. 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 I see. Hmm. Ah, there are many different ways people do annealing schedules, as they're called. You could just have it march along a defined schedule, and then it starts out just jumping wildly, and then eventually it settles in somewhere as as the temperature decreases. There are other approaches where you seed a modulator, so to speak, on the temperature that says if this large jump produces a dramatic increase, then that's not desirable. If it's a small increase, it is desirable. So I'm going to stay here and do more local search. Another approach that people have taken is you start out with large jumps and you're effectively probing. And with that set of large jumps, you keep a memory of what the objective measure was in neighborhoods of the landscape. And then next time you're going to select an area to explore, you bias that selection probability based on this coarse measure of neighborhoods around the search space. And so, in effect, and this is probably a bad visualization, but it's the best one I can think of. If I were to divide up this landscape into regions, just looks like an eight puzzle now, and I said, let me take large jumps. That's a great question. I could jump randomly, and that random jump could take me all over the landscape, right? And at each locus, I compute my objective measure. And then when I go to do some exploration, I say I'm going to do more local search, but I'm going to bias where I local search based on that more coarse measure. So there's all sorts of ways people do that. Effectively, they divide the search regime into a probing phase where you have large jumps, and then you have an exploration phase where you have small jumps. And in that case, this tessellation just gives you a region where you're going to do your search, right? So then what you could do in your next round, you say, I'm going to look at the best region. Let's say the best region was this one. Now I'm going to change my temperature schedule to have, say, medium jumps. And those medium jumps are going to be started in this region, starting at that place I know is good in that region. So then I'm going to take medium jumps. So it's almost like, for lack of a better example, a quad tree, right? But you're constructing it incrementally and you're seeding where you proceed with your medium jumps based on the information you get from those coarser jumps. Does that make sense? Answer your question? There's no one way to do it. So I can't say, well, you do it this way, right? Um, in the literature, it's about controlling this temperature. And so the probe gives you coarse measurements of how good and how bad and where that good and bad is in the landscape at a coarse level. And then when you switch your schedule to medium jumps, you choose a location, right? That's one way people have done it. There are many, many, many different ways. Plain vanilla simulated annealing just starts with the large temperature. It says make large jumps and then hope to get lucky that when you decrease the jump size to medium and then small, get lucky that you're just in the right place. That's one way of doing it. But you're welcome to also use the information that you gain from these probes in just about any way. There's no one way people have done this. Okay. The literature is full of hundreds of different examples of variations people have tried. Okay. And so that's kind of a hard question to answer discreetly, but the first level approximation of simulated annealing just has a schedule. And once that schedule says go from large jump to medium jump, relies on you being in quote unquote the right place at the right time, which is never how people do it in practice. You always use information that you encounter along the way during your larger jumps to seed where you're going to do the local exploration. Okay. All right. Any other questions? No? All right. So in essence, when you probe or make your large jumps, you're seeking out so-called basins of attraction. And these basins of attraction you can think of as these bowls, if you're looking for gradient descent, where once you reach the edge of this bowl, the local search is going to get you to that local minimum or local maximum, depending on if you're solving hill climbing or gradient descent. And then the small jumps are almost like hill climbing, like gradient descent or gradient ascent. Okay. All right. So this is the pseudocode for simulated annealing. And again, simulated annealing is more like a family of approaches. It's not just one way of doing it. And so the idea then is you have some schedule or way of varying your temperature. And in this case, you're looking at how much of an improvement that jump to another location, your successor generation, has that you've seen. And if you have an improvement, then you pursue this next landing spot as your next state from which you retry. Otherwise, you select your next location based on some probability. Now, that probability might be based on this notion of successors, or it could just be based on notion of any instantiation from your state space. Because if you can set a probability on something, you can certainly set a probability on regions of your state space once you've defined it, right? And so again, this is abstracting from search more generally to tools from optimization. Okay? All right. Any questions? No? Okay. So in this case, what simulated annealing does, and through the design of your temperature, whether it's hierarchical, whether you're using information from your probes, or whether you're just a blind schedule, it's how you engineer the schedule that determines whether or not you're probing or you're doing greedy selection, right? Greedy selection is a special case where you're just 100% probability on the maximum, right? Okay, any questions? No? All right. So another variation is what's called local beam search, and I have some visualizations for you. We have our state space along the XY plane, and then we have our landscape here, whose value is measured along the Z-axis. And so with beam search, you start with some number K randomly selected states. And from these randomly selected states, so it's almost like you're probing, you're going to generate their successors. Okay. So once you generate their successors, all right, you're going to check to see if one of those successors you generated over these K-many random states, if they're a goal, right? If it's a goal, that's the best case. You end. Then from those successors that you generated, you're going to select the K best of them, holding on to them. And from those K best successors, again, you repeat. So in essence, you can think of it as a search concurrently from many different places at the same time. And you're selecting the top K most fruitful states that you're going to continue to explore, right? And certainly you could do something like that in Pac-Man, and it would be fruitful for large mazes. But then the question is, how big should K be? Now, because it's random, ideally, you're going to get some uniform coverage across your state space, but you want to make sure that K is large enough for some definition of large enough to give you good coverage across different neighborhoods or regions within your state space. Because you don't want to concentrate these samples, these probes, in one tiny corner, that corner where the ghosts are within 5 moves of you, right? Because that just represents a very tiny region of your space. You want to have coverage so that you can have an opportunity to arrive upon a goal. Because goals generally just aren't in one place, especially if there are multiple goals in your state space. Okay. So another one is called stochastic beam search. Instead of selecting your successors, okay, and doing this top K, you're going to give those less desirable successors an opportunity to be selected. Less desirable, meaning that you have a selection probability, and that selection probability, in this example, let's say you had three successors, one had an objective measure one, the others two, the others three. You're going to weight their selection for further pursuit based on a probability proportional to their objective measure. And so what this does is it says, all right, well, I'm going to pursue the best successor if it were hill climbing in this case, but I'm going to have an opportunity to make a suboptimal selection because sometimes the best solution requires a suboptimal step along the way. Does that make sense? Any questions? No? All right. So then the last one, in the next 2 or 3 minutes, is genetic search. And genetic algorithms aren't as popular today, but they're still used in some domains, like um, workforce route assignment and stuff like that. In a genetic algorithm, it kind of looks like randomized beam search. And this is also in the book. You sample multiple states. So you start with your state space and you just sample across it. So you don't really have a notion of a starting place. And then from that sample of states, you're going to perform their evaluative measure. And then you're going to have a round of so-called survival of the fittest. You're going to select some population where you define the size of the population of this notion of the best states. Okay. And then after that, you take individual states from your population or set of states, and then you're going to perform crossover. Now, crossover is like genetics, mating. You have certain parts of the state space, this genetic material, that gets combined to create new states, right? So you're going to spawn new states by taking parts of the best states from this round of so-called elitist selection. And so, in essence, this elitist selection kind of looks like a priority queue. But in this case, you define some measure of what it means to be a good state beyond just a priority queue. And once you do crossover, then you're going to, for those newly created individuals or states, you're going to perform mutation. You're going to randomly take parts of their state description and you're going to randomly change it, right? And that randomization is kind of like Brownian motion. You're going to introduce a move that otherwise wouldn't have been propagated from selecting the best states. Because again, sometimes you want to explore, sometimes you want to select some notion of the best or the worst. Okay. And so this is part of a trade-off in any sort of optimization problem called exploration versus exploitation. The exploitation refers to the maximization or minimization of some evaluative measure. The exploration talks about a randomized choice, and this randomized choice might induce an improvement. It might not induce an improvement, but the idea is to explore around because it might lead to a good solution. Take, for example, if you have a music recommendation service, you don't always want to have recommendations for music for things that you already like. Sometimes you want it to make a choice that is outside of what you would like, the exploration, because you might discover you like something different from what you already listened to. And that's a classic example of exploration versus exploitation. And so with genetic algorithms, we think of this as a kind of multi-frontier search. It's similar to stochastic beam search. You initialize a bunch of randomly selected states, and then you perform this elitist selection, the top K of them, and then you do your crossover. And I tried to visualize crossover here. You take some states starting from the two randomized initial ones, and then you build a new state, which is some combination of subsets or positions from one good solution and another to produce a new individual. And then you wiggle it a little bit, this mutation, to change it a little bit, because that might discover for you some alternative that you otherwise wouldn't have considered when you perform the maximization, this elitist selection. Does that make sense? Any questions? No? And you could absolutely do this with Pac-Man. We're not going to do this with Pac-Man, But after the class is done, you're welcome to your heart's desire to try out some of these methods and also look at how it affords you performance improvements, especially as the maze gets bigger and the environment gets more complex. Okay, so we're at time, and that consequently is all I had to say. I'll see you all tomorrow, and have a great, yes, rest of your week. One more day. All right. Take care.